How could Newton decipher gravity as adequate to allow us to fly from the Earth to the Moon anytime? Get yourself lost in the ticking hands of time, examining whether we could decipher it. This is basically the tip of the common lump of ice on its head. His exposure isn't just speculation. A key could open the approaches to the mysteries of the universe, revealing a universe more versatile and moving than we ever naturally suspected for even one moment. Imagine. How does Brian Cox's new speculation challenge our standard understanding of time, and what are the possible implications for our perception of reality? Join us on a captivating exploration through the files of time itself as we dive into Brian Cox's recently uncovered monumental theory on time in the vast universe. Mysteries are waiting to be uncovered, and some of these secrets involve fascinating concepts like time and gravity, which are fundamental elements of our existence. Imagine a reality where time behaves in surprising ways. It can slow down or speed up. Furthermore, the force that keeps us on the ground might not be what it seems. This is the realm of Albert Einstein's theory of relativity, where our understanding of time and gravity takes an unexpected turn. Albert Einstein, a remarkable name, gave us a revolutionary way of looking at the universe through his theory of relativity. His work laid the foundation for understanding how time behaves under different conditions, especially when traveling at incredibly high speeds. It all began during the 20th century when Einstein proposed two historic theories: the special theory of relativity and the general theory of relativity. The special theory of relativity, published in 1905, fundamentally changed our understanding of reality. It tells us that the laws of physical science remain the same for all observers who aren't accelerating, regardless of their movement. This theory introduces the concept of relativistic effects, including the famous idea that time can stretch or slow down under certain conditions. One fascinating thought experiment used to explain time dilation is the light clock. Imagine being inside a spaceship moving incredibly fast, almost at the speed of light. Inside the spaceship, there's a light beam bouncing between two mirrors, perpendicular to the direction of motion. According to the laws of physics, the speed of light is constant for all observers. So, the light beam appears to travel a longer diagonal path to an outside observer. The time it takes for the light to travel this path is the same for both observers. However, since the path is longer for the external observer, it seems like it would take more time for the light to complete its journey. This apparent time difference between the two observers is what Einstein called time dilation. Time slows down for the observer moving relative to the stationary observer. Understanding how things change when they move fast, known as relativistic effects, is not just a theoretical concept. Scientists use massive machines like particle accelerators such as the Large Hadron Collider to make particles travel nearly as fast as light. At these speeds, we must account for time in a unique way to make accurate predictions and measurements. Einstein's special theory of relativity revolutionized our perception of the universe, particularly concerning time and motion. Challenges our intuitive understanding. For instance, it posits a maximum speed that nothing can exceed: the speed of light. Events that seem simultaneous to us might not appear the same to someone moving near the speed of light. Another concept, length contraction, suggests that objects appear shorter in the direction of motion when observed from a stationary frame of reference. Then there's the famous equation, which demonstrates the equivalence of energy and mass, a cornerstone of understanding nuclear reactions and particle physics. In practical applications, special relativity isn't just a theoretical framework. It's crucial for modern technology like GPS satellites experience slight time dilation due to their movement, and if this effect weren't accounted for, GPS calculations would be inaccurate. Special relativity teaches us that time isn't uniform. It depends on motion, challenging our perception of reality. Enter Einstein's general theory of relativity, introduced in 1915. This theory delves deeper into the relationship between gravity and the fabric of the universe. It redefined gravity not as a mysterious force pulling objects, but as the warping of space-time itself. Imagine the universe as a four-dimensional fabric combining 3 dimensions of space and 1 of time. Massive objects like stars and planets bend this fabric, creating the effect we perceive as gravity. General relativity suggests that gravity isn't a force but the result of objects moving along the curves of spacetime. For example, Planets orbit the Sun because they follow the curvature created by the Sun's mass, similar to how a ball rolls toward a heavier object on a stretched fabric. One monumental confirmation of general relativity occurred during a solar eclipse in 1919. Sir Arthur Eddington and his team observed how light from distant stars bent as it passed near the Sun. The observations matched Einstein's predictions, cementing the accuracy of his theory. Assumptions spreading out the authenticity of the speculation, comparatively as development, can change how we experience time. As demonstrated by remarkable relativity, gravity likewise impacts time. Where gravity is particularly strong, time moves more slowly compared to regions with weaker gravity. For instance, if you were standing close to a massive object like a black hole, your clock would tick more slowly than one set far away from the strong mass. General relativity introduces the concept of black holes, which are regions where gravity is so intense that nothing, not even light, can escape from them. The edge surrounding a black hole is known as the event horizon, resembling a final boundary. Once something crosses this limit, it gets drawn into the black hole with no chance of returning. Einstein's theory of general relativity has significant implications for how the universe is structured. Initially, he introduced a cosmological constant in his equations, believing the universe to be static. However, when the universe was discovered to be expanding, he referred to this as a major oversight. The idea of an expanding universe, derived from general relativity, forms a crucial aspect of the Big Bang theory, which explains how the universe began. Another important concept from general relativity is gravitational waves. These are ripples in the fabric of spacetime caused by massive objects moving rapidly, such as when black holes or neutron stars merge. In 2015, scientists at the Laser Interferometer Gravitational Wave Observatory, LIGO, directly detected gravitational waves, providing evidence for another aspect of Einstein's theory. Over time, scientists have conducted numerous experiments to confirm the validity of general relativity, and each time it has proven accurate, whether through observing planetary motions, the bending of starlight, or detecting gravitational waves. While challenging the idea of gravity might seem surprising, it is common in the realm of physics to question established theories. Researchers like Brian often explore alternative ideas in the field of gravity. One such idea challenging standard gravity is called modified Newtonian dynamics, MOND, which suggests that gravity behaves differently at low speeds, particularly in galactic systems, without requiring dark matter. Instead of introducing invisible matter, MOND proposes that gravity strengthens at low speeds. The debate on gravity also involves the perplexing concepts of dark matter and dark energy, which were introduced to explain certain phenomena in space. Critics argue that these aren't essential and that alternative theories could account for what we observe. Some researchers exploring alternatives to Einstein's theory investigate possibilities such as dark particles or forces that might reshape our understanding of gravity. It is essential to emphasize that novel ideas in science are not dismissed outright. Instead, they are rigorously tested to determine their validity. For instance, Einstein's idea of time in four-dimensional space, where time travel might be limited by the speed of light, has been creatively examined, along with concepts like wormholes and shortcuts through spacetime. Stephen Hawking's chronology protection conjecture suggests that traveling into the past appears impossible from a physics perspective. Ongoing experiments and observations aim to determine whether these new theories can explain phenomena like the strength of gravity in a manner consistent with current knowledge. While various ideas have been explored, none have convincingly replaced the established principles of gravity. Questioning and testing are critical to challenging established concepts, fostering further research, and deepening our understanding of the universe. In the realm of gravity theories, general relativity remains the most robust and successful one. Despite challenges and alternative ideas, it consistently performs well in tests and explains numerous phenomena, such as planetary motions and the bending of light around massive objects. Einstein's special theory of relativity also suggests that time can behave differently depending on how you're moving. Now, let's explore how this concept affects real-world scenarios, especially in space travel. Space travel is exciting yet challenging because space is vast. According to Einstein's theory, the speed of light is the fastest anything can travel, making interstellar journeys a significant challenge, even with advanced technology, due to the lengthy time required to reach the nearest stars. Consider the famous twin paradox to understand how time changes during space travel. Imagine one twin remains on Earth while the other embarks on a high-speed journey to a distant star. When the space-traveling twin returns, they find that less time has passed for them than for their twin on Earth. This means they have effectively traveled into the future. Time is crucial for astronauts because, on long missions, time slows significantly. If astronauts were to visit nearby stars where time slows dramatically, they might age more slowly than people on Earth. While this may sound like science fiction, it is a real consequence of the theory of relativity. Imagine if humans sent a crew to a star system not too far away. Due to the immense distance, the trip could take many years, even at high speeds. For the astronauts aboard the spaceship, time would feel shorter due to the time dilation effect. However, on Earth, a much longer time would have passed. Time dilation affects not only living organisms but also technology. Computers and communication systems on rockets must account for time dilation to ensure accuracy and proper functioning. Space travel at high speeds presents real challenges, such as prolonged confinement, exposure to cosmic radiation, and psychological effects from being away from Earth for extended periods. In our daily lives, we observe the effects of time dilation in the Global Positioning System, GPS. GPS relies on the precise timing of signals from orbiting satellites. Since these satellites experience time dilation, it is essential to account for these effects to ensure accurate GPS calculations. Failing to do so would significantly impact navigation systems' precision. Now let's explore why time moves in one direction. Time governs our lives in the universe, moving from the past to the present and into the future. This one-way flow of time is fundamental to our existence. To understand this, we examine entropy, a measure of disorder or randomness in a system. Entropy tends to increase over time, driving the forward motion of time. The second law of thermodynamics expresses this relationship, stating that in any isolated system, total entropy will either increase or, at best, remain constant. In simple terms, entropy naturally tends to grow and does not decrease on its own. Recognizing that things become more disordered over time helps us perceive the one-way progression of time. For example, imagine a deck of cards neatly arranged. If we shuffle them, they become disorganized and random. This transition from order to chaos illustrates how time moves in one direction, as seen in natural phenomena like melting ice or a stirred cup of coffee mixing evenly.